efficient equilibrium and the LP relaxation. In this section, we return to discuss combinatorial options with general evaluations, and we will study the linear programming relaxation of the winner determination problem in such functions. We will also define the economic notion of a competitive equilibrium. With item prices or Walrasian equilibrium, although these notions appear to be independent at a first glance, we will describe a strong connection between them. In particular, we will prove that the existence of a Walrasian equilibrium is a sufficient and necessary condition for having an integer optimal solution for the linear programming relaxation, i.e. no integrality gap. One immediate conclusion is that in environments where Walrasian equilibria exist, the efficient allocation can be computed in a polynomial time. The linear programming relaxation and its dual. The winner determination problem in combinatorial options can be formulated by an integer program. We present the linear programming relaxation of this integer program and denote it by LPR in the integer program constraint. 11.6 would be replaced with the xis in the set either 0 or 1. The linear programming relaxation LPR is to maximize the summations of xis times vi of s, summing for all those I in n and s, which is a subset, or equals to n, such that the summations of xis is less than or equals to 1, summing for all index I in n and s such that j is in s, for all j in n, and summation for xis, which is less than or equals to 1, summing for all s, which is a subset or equals to n, and for all I in n. The last one is xis, which is greater than or equals to 0, for all I in n, and s, which is a subset or equals to n. So it could be replaced by xis is either 0 or 1. In the integer program, each variable xis equals 1 if leader I receives the bundle s and 0 otherwise. The objective function is therefore maximizing social welfare. Condition 11.4 ensures that each item is allocated to at most one leader, and the condition 11.5 implies that each player is allocated at most one bundle. Solutions to the linear program can be intuitively viewed as fractional allocations, allocations that would be allowed if items were divisible. While the LP has exponentially in n many variables, it still has algorithmic implications. For example, in the case of single-minded biders, only a single variable xi star for each bidder I is required, enabling direct efficient solution of the LP. In section 11.5.2, we will see that, assuming reasonable access to the valuations, the general LP can be solved efficiently as well. We will also consider the dual linear program. The dual linear programming relaxation, DLPR, is to minimize the summations of UI, the summing for all index I in n, plus the summations of pj, summing for all j in n, such that UI plus the summations of pj summing for all j in s is greater than or equals to vi of s. This is for all I in n and for all s, which is a subset equals to n. And another constraint is that UI is greater than or equals to 0 and the pj is greater than or equals to 0 for all I in n and for all j in n. The usage of the notations pj and ui is intentional, since we will later see that at the optimal solution, these dual variables can be interpreted as the prices of the items and the utilities of the bidders. Walrasian equilibrium. The fundamental notion in economic theory is the notion of competitive equilibrium, a set of prices where the market clears, i.e. the demand equals the supply. We will now formalize this concept that will be generalized later in section 11.7. Given a set of prices, the demand of each bidder is the bundle that maximizes her utility. There may be more than one such bundle, in which case each of them is called a demand. In this section, we will consider a linear pricing rule where a price per each item is available, and the price of each bundle is the sum of the prices of the items in this bundle. Definition 11.11. For a given bidder valuation VI and a given item prices P1, P2, P3, and Pn, a bundle T is called a demand of bidder I if, for every other bundle S which is subset equals to M, we have that VI of S minus the summations of Pj summing for all j in S is less than or equals to VI of T minus the summations of Pj summing for all j in T. The Walrasian equilibrium is a set of market clearing prices where every bidder receives a bundle in his demand set, and the unallocated items have zero prices. Definition 11.12. A set of non-negative prices P1 star, P2 star, and so on to Pm star, and an allocation S1 star, S2 star, and so on to Sm star of the items is a Walrasian equilibrium if for every player I, Si star, is the demand of bidder I at prices P1 star, P2 star, and so on until Pm star, and for any item j that is not allocated, i.e. j is not in the union of the Si star summing union for all I starting from 1 to n, we have that Pj star equals to 0. The following result shows that Walrasian equilibria, if they exist, are economically efficient, i.e. they necessarily obtain the optimal welfare. This is a variant of the classic economic result known as the first welfare theorem, but for environments with indivisible items. Here we actually prove a stronger statement. The welfare in the Walrasian equilibrium is maximal even if the items were divisible. In particular, if a Walrasian equilibrium exists, then the optimal solution to the linear program relaxation will be integral. Theorem 11.13. The first welfare theorem, that P1 star, P2 star, and so on to Pm star, and S1 star, S2 star, and so on to Sn star be a Walrasian equilibrium, then the allocation S1 star, S2 star, until Sn star maximizes social welfare. Moreover, it even maximizes social welfare over all fractional allocations, i.e. let the set of xi S star with index I and S paired be a feasible solution to the linear programming relaxation. Then the summations of a Vi of Si star summing with index I starting from 1 to n is greater than or equals to the summations of a xi S star times Vi of S summing with index I in n and S, which is a subset equals to n. Proof. In a Walrasian equilibrium, each bidder receives his demand. Therefore, for every bidder I and every bundle S, we have Vi of Si star minus the summations of Pj star summing for all j in Si star, which is greater than or equals to Vi of S minus the summations of Pj star summing for all j in S. Since the fractional solution is feasible to the LPR, we have that for every bidder I, the summations of xi S star is less than or equals to 1 summing for all S. This is constraint 11.5, and therefore Vi of xi star minus the summations of Pj star summing for all j in Si star is greater than or equals to the summations of xi S star summing for S, which is a subset equals to M, times Vi of S minus the summations of Pj star summing for all j in S. The theorem will follow from summing inequality 11.10 over all bidders and showing that the doubling summation of Pj star with the outer summation summing for all I in N and inner summation summing for all J in Si star is greater than or equals to another doubling summation with the outer summation summing for I in S and S, which is subset equals to M with the term XIS to the star, and the inner summation summing for index J in S with the term PJ star. Indeed, the left-hand side equals the summations of PJ star summing with J starting from 1 to M, since S1 star, S2 star, and so on until Sn star is an allocation in the prices of unallocated items in the Walrasian equilibrium are 0, and the right-hand side is at most the summations of PJ star summing with J starting from 1 to M, since the coefficient of every price PJ star is at most 1 by constraint 11.4 in the LPR. Following is a simple class of valuations for which no Walrasian equilibrium exists. Example 11.14. Consider two players, Alice and Bob, and two items, A, B. Alice has a value of 2 for every non-empty set of items, and Bob has a value of 3 for the whole bundle, the set AB, and 0 for any of the singletons. The optimal allocation will clearly allocate both items to Bob. Therefore, Alice must demand the empty set in any Walrasian equilibrium. Both prices will be at least 2, otherwise Alice will demand a singleton. Hence, the price of the whole bundle will be at least 4. Bob will not demand this bundle, and consequently no Walrasian equilibrium exists for these players. To complete the picture, the next theorem shows that the existence of an integral optimum to the linear programming relaxation is also a sufficient condition for the existence of a Walrasian equilibrium. This is a variant of a classical theorem known as the second welfare theorem that provided sufficient conditions for the existence of a Walrasian equilibrium in economics with divisible commodities. Theorem 11.15. The second welfare theorem. If any integral optimal solution exists for LPR, then a Walrasian equilibrium whose allocation is the given solution also exists. Proof. An optimal integral solution for LPR defines a feasible efficient allocation S1 star, S2 star, and so on to Sn star. Consider also an optimal solution P1 star, P2 star under Pn star, U1 star, U2 star under Un star to the LPR. It will show that S1 star, S2 star until Sn star, P1 star, P2 star until Pn star is a Walrasian equilibrium. Complementary slackness conditions are necessary and sufficient conditions for the optimality of solutions to the primal linear program, and is due because of the complementary slackness conditions. For every player I, for which xi si star, which is greater than 0, i.e. xi si star equals to 1, we have that the constraint 11.8 is binding for the optimal dual solution, i.e. Ui star is equals to Vi of Si star minus the summations of Pi star summing for all j in Si star. Constraint 11.8 thus also shows that for any other bundle S, we get Vi of Si star minus the summations of Pi star summing with for all j in Si star is greater than or equals to Vi of S minus the summations of Pi star summing for all j in S. Finally, the complementary slackness conditions also imply that for every item j, for which constraint 11.4 is strict, i.e. the summations of xis, summing for all index I in n and s, such that j in s. The result of the summation is less than 1, which for integral solutions means that the item j is unallocated when necessarily pj star is equals to 0. The two welfare theorem show that the existence of a Walrasian equilibrium is equivalent to having a zero integrality gap Corollary 11.16. The Walrasian equilibrium exists in a combinatorial option environment given only if the corresponding linear programming relaxation admits an integral optimal solution.